All right, the second set of relay tracts that we're going to talk about is the divergent pathways, also known as the medial pain system. So the divergent pathways, they transmit information to various areas of the brainstem and cerebrum. They are the affective dimension of pain, meaning they are the emotional, how we feel about pain, how it affects us, how it affects our sleep and our arousal and our attention. They are not somatotopically organized as the conscious relay pathways are, so it's not as localized. It's not as high fidelity. There are conscious and unconscious tracts in the divergent pathways. So some of the things we sense, some of the things we don't. The divergent pathways are largely C fibers, free nerve endings going to the dorsal root ganglion in the spinal cord, to the medial pain system, which we'll talk about the 3 tracts in the medial pain system, and they go to various areas in the brain. So slow pain travels within the anterolateral columns. So we talked about the fast pain, the spinothalamic pain, traveling in the conscious relay pathways. That's the discriminative fast pain. In the divergent pathways, we have the slow pain, the C fibers. So in the conscious pathways, it's those A delta fibers. In the divergent pathways, it's those C fibers. So the 3 spinal tracts, and we're going to look at the name of these tracts and see see where they go by their names. So the first one is the Spinomesencephalic Tract. So let's break that word down so it makes sense. Spino means it starts in the spine. Mes is middle, and encephalic is brain. So spine to the midbrain. That makes sense, right? So in the midbrain, we know that is some of our autonomic responses, some of our vital senses. So the information, the pain information that ascends via C fibers through the spinomesencephalic tract, it causes you to turn your head and eyes towards the source of pain, and it activates descending tracts that control pain. We're going to talk about in Chapter 7 an area called the periaqueductal gray area. You don't have to know that right this second, but abbreviated PAG. So part of our descending pain control tracts are activated in the midbrain when sensation from those C fibers arrives in the spinomesencephalic tract via that tract into the midbrain. Okay? So the next tract that travels within the anterolateral medial pain system is the Spinoreticular Tract. So it goes from the spine to the reticular activating system. So the reticular activating system controls our arousal, attention, sleep, and wake cycles. Those arousal, attention, sleep, and wake cycles are modulated by the reticular formation. That's why severe pain will wake you from sleep. So a lot of times after knee surgery, almost everybody tells me that they have trouble sleeping after knee surgery. The pain wakes them up. We'll hear that a lot in the clinic. The pain woke me up in the middle of the night. That is slow pain traveling in the anterolateral columns via the spino-reticular system. That pain from the spine is going right to your reticular formation, and it's keeping you awake. That's not fair, right? But there you go. So the spino-reticular system, it makes sense. It travels from the spine to the reticular system. It's afferent. It disrupts our arousal, attention, and sleep-wake cycles. So for attention, when you're in pain, some of those areas are in a pain meeting, and you have a harder time concentrating and a harder time paying attention. So we'll talk more about pain in Chapter 7, but that's a really important component of those slow pain tracts. The third tract that we're going to talk about is the spino-limbic tract. So the limbic system goes from the spine to the limbic system. The limbic system is our emotions and our emotional memory. It's slow pain information. It goes through the thalamus and then projects to various areas involving emotion, sensory integration, and personality. So very interesting stuff going on in the spinal limbic tract regarding pain. And in Chapter 7, when we're talking about pain control systems, I'm going to address this and how emotion and memory of emotion integrates with sensory information to either turn up your pain response or turn down your pain response. Very interesting area. So an example of the slow pain using these different tracts, you fall on your outstretched hand and you break your ulna. So you automatically look at the injured area, that's the spinomesencephalic tract. Automatic reflexes pull your arm, withdraw your arm from the source of injury. So a lot of times you'll pull your arm towards you to protect it. You might faint because information going in the spinal reticular system affects your arousal, attention, and sleep-wake cycle. It might cause you emotional distress because of information traveling in that spinal limbic system. And your whole hand might ache because that slow pain information is not very closely localized like the fast pain is. So your reactions to the pain integrate a lot of different areas, and that's really going to come into play when we talk about anti-nociception or pain control systems. Okay, so we're just going to review that information. Divergent pathways, the reason it's called divergent is because the information is transmitted to many locations in the brainstem and cerebrum. And it uses pathways with varying numbers of neurons. So a lot of times it's slower than the fast pain pathways. Because the fast pain pathways, it's a three neuron path. The divergent pathways, it can be varying numbers. Sensory information is used at both the conscious and the unconscious levels. So aching pain is a form of sensation that's transmitted via divergent pathways in the central nervous system. So a lot of times that fast spinothalamic pain, it's closely localized. You can tell right where it is. The slow aching pain is more diffuse. You can't necessarily localize exactly where the pain is. And so that's a difference between acute, fast spinothalamic pain and slow, divergent spinolimbic and spinoreticular pain. So it's a different form of pain. It's not as easily localized. That's the stuff that bugs you and keeps you up at night because of that spinoreticular pathway, though. So heat and cold are detected by specialized nerve endings of small myelinated and unmyelinated neurons, or relatively unmyelinated. A delta fibers carry impulses produced by cooling. C fibers carry information regarding heat. So we're going to feel cold faster than we feel heat because A delta fibers are faster, right? Pain is composed of both sensation and the emotional response to the sensation. So pain, it's not like, oh, a nociceptor is activated and we get the same pain sensation in the brain. My pain is going to be different from your pain. My emotional response is going to be different from somebody else's emotional response. And when we talk in the pain chapter, I'm going to talk more about this. Very interesting area of study, particularly in physical therapy, because as we said in modalities class, pain is often the reason that sends people into physical therapy or causes people to seek a referral to physical therapy. Pain is one of the most common reasons that people seek physical therapy. So the nociceptive receptors are neurons that receive or transmit information about stimuli that threaten to damage or damage tissues. Those are the, so it's not just damage, it's the threat of damage that can cause pain. So you can have pain without actual tissue damage. That's a really good thing to remember for physical therapy. So fast pain or spinothalamic pain is the initial immediate sharp sensation that indicates the exact location of the injury. Slow pain or spinolimbic pain is the dull, throbbing ache following fast pain that's not well localized. because it goes in those divergent systems. The fast localized pain is the lateral pain system using a 3-neuron pathway. Primary neuron brings information to the dorsal horn of the spinal cord. Axons of the secondary neurons cross the midline and project from the spinal cord to the thalamus. The tertiary neurons project from the thalamus to the cerebral cortex. So that's our fast pain, spinothalamic pain. Here's the little pathway. Fast pain versus slow pain. When the fast pain information reaches the somatosensory cortex, the person is consciously aware of sharp pain in a specific location. It's well localized. If tissue damage has occurred, fast pain is followed by slow aching pain. So if you have something with minimal tissue damage, and I'm going to use a paper cut as an example. With a paper cut, it hurts like heck when you first do it, right? It's fast pain, well localized. There's not a lot of tissue damage with a paper cut, and so you often don't have that slow aching throbbing pain, because the slow aching throbbing pain comes from tissue damage. So the onset of slow pain is usually later than fast pain because the impulses travel on smaller, less myelinated or unmyelinated axons. Okay? So fast pain, A deltas in the spinothalamic system, well localized. Slow pain, C fibers, less myelinated, smaller, in the spinal limbic system, and it's that slow aching, less localized pain. So the medial pain system is those divergent ascending network of neurons. They use several pathways, variable numbers of projection neurons, not a 3-neuron pathway like fast pain. The activity of the medial pain system elicits affective, meaning emotional, motivational, withdrawal, arousal, and autonomic responses. So lots of different responses from the medial pain system because it's a divergent pathway. It goes to many different areas of your brain. The information is not somatotopically organized, so slow pain cannot be precisely localized, unlike fast pain. Very interesting. The first neuron is a small unmyelinated or less myelinated C fiber. The receptors are free nerve endings that are sensitive to noxious heat, chemical, or mechanical stimulation. High threshold C fiber endings can become sensitized with repeated stimulation. So things that sensations that wouldn't have been painful to begin with, once those C fibers are sensitized, you can have more pain associated with it. And we will talk more about that in Chapter 7 as well. The ascending projection neurons, the axons go to the midbrain, the reticular formation, and the limbic system via 3 tracts in the anterolateral spinal cord. The spinomesencephalic, so spine to midbrain, spinoreticular, spine to reticular formation, and spinolimbic, spine to the limbic areas. Okay? The tracts are parallel ascending tracts. The information in the spinal limbic tract is perceived as pain. The other ones are perceived as changes in your arousal and awareness and sleep-wake cycle, and the spinomesencephalic is changes from the midbrain. It could be descending controls, or it could be movements and autonomic responses. So it's not a conscious perception. The spinomesencephalic tract carries nociceptive information to the 2 areas in the midbrain, and you don't need to memorize these, the superior colliculus and the periaqueductal gray area. The periaqueductal gray area is part of the descending pain control system, which we will talk about in Chapter 7. The reaction from the spinomesencephalic tract is involved in turning the head and eyes towards the source of the noxious input and activating those descending pain control tracts. So that's the main purpose of stimulating that tract. The spinoreticular tract are ascending neurons that synapse in the reticular formation, which is a neural network in the brainstem that includes the reticular nuclei and their connections modulating arousal, attention, and sleep-wake cycles. So pain keeps you awake. There you go. There's the neurological explanation for why pain keeps you awake. The spinolimbic tract, the axons of the spinolimbic tract transmit slow pain information to to the medial and interlaminar nuclei in the thalamus. You do not need to know the individual nuclei. So we can just say it goes from there to the thalamus. Slow pain pathways provide information that produce automatic movements and autonomic and emotional responses to noxious stimuli. Activity in the spinoreticular and spinal limbic tracts often result in arousal changes, withdrawal, autonomic, and affective responses to pain, meaning emotional responses to pain. The information transmitted, when they say the phylogenetically older pathways, that means those are the ones that developed earlier in our evolution. They're older pathways to the reticular formation, non-specific nuclei of the thalamus, subcortical nuclei, and the hypothalamus. This information that doesn't reach conscious awareness contributes to arousal, gross localization of pain, and autonomic regulation. So temperature information is often regulated in the hypothalamus autonomically. So do we need to step up our metabolism to get warmer? Do we need to slow it down to cool it down? So that happens unconsciously in the hypothalamus. Okay, we're going to wrap this section up, and in the next section we're going to talk about the unconscious relay pathways.